December 1944, Mojave Desert, California. A cold wind swept across the barren sand as a small group of men stood behind a concrete barrier, their breath visible in the frigid dawn. The sound that followed was unlike anything they had ever heard. Not the steady hum of a propeller, but a rising guttural roar that seemed to come from the very earth itself. A silver shape lifted from the launch rail, fire streaming from its tail. The missile screamed across the horizon at a speed no human pilot could match. For a few seconds, no one spoke. Engineers in olive drab coats watched the vapor trail curve upward and vanish. In that silence, one truth settled in. America had just entered a new chapter of warfare, one driven not by courage in the cockpit, but by engines and equations. Far across the Atlantic, in Peenemünde, German scientists would soon receive intelligence that made them stare in disbelief. The Allies had created a jet-powered missile, and the race for the future of war had just begun. By late 1943, the balance of the Second World War had begun to tilt, but not without cost. The Allies were gaining ground in Italy, and the Soviet advance in the east was relentless. Yet over the skies of Europe, the Germans still held terrifying cards. From the laboratories of Peenemünde on the Baltic coast came weapons that seemed almost unreal. The Vergeltungswaffen, or weapons of vengeance. The V-1 flying bomb and its successor, the V-2 rocket, struck London with mechanical precision and psychological force. To many civilians, it felt like the future itself had turned hostile. The V-1, in particular, was a strange creature, a pilotless aircraft powered by a pulse jet, its engine coughing with a sinister rhythm. It could reach nearly 400 miles per hour, fast enough that few Allied fighters could intercept it. The V-2 was even more astonishing, a ballistic missile that soared beyond the edge of the atmosphere before plunging toward its target at supersonic speed. No warning, no defense, only devastation. In Washington and London, these developments sent shockwaves through military leadership. How had Germany achieved such technological leaps while under siege? How close were the Allies to their own breakthroughs? For the United States, still ramping up its air power, this was more than a question of science. It was a matter of survival. General Henry Hap Arnold, commanding general of the U.S. Army Air Forces, understood it immediately. In private meetings, he warned that the war would not be won by numbers alone. Superiority in air power, he argued, means superiority in research. The enemy's secret weapons could only be countered by something equally revolutionary, and so, under his direction, a network of scientists, engineers, and military officers began to converge around one audacious goal: to harness jet propulsion and guided flight for the Allies. It was a time when laboratories turned into battlefields of their own. At Wright Field in Ohio, experimental departments studied fragments of captured German aircraft. At Caltech in California, a small group of physicists worked under the newly formed Jet Propulsion Laboratory, a name that would one day echo across space history. In scattered airfields and makeshift hangars, men who had once designed racing engines now studied airflow equations and combustion chambers. The urgency was relentless. Reports of German V-1 attacks filled newspapers in mid-1944, describing buzz bombs that screamed across the sky before falling silent, and then exploding. Every explosion was a reminder that the world had crossed into a new kind of war. Traditional air defenses, radar, even anti-aircraft guns were becoming obsolete. The battlefield was changing faster than anyone could adapt. In the United States, industrial production had already reached its peak. Factories built bombers by the hour and trained pilots by the thousand. Yet none of it would matter if Germany's technological advantage grew unchecked. A handful of scientists realized that the old paradigm, human pilots fighting machine to machine, was ending. The future would belong to unmanned weapons, to the cold precision of jet propulsion and remote guidance. Amid that realization, American engineers began studying the principles of pulse jet engines. They were crude yet effective. No moving parts, only tubes, valves, and fire. If they could build something like the German V1, they could learn from it, perhaps even improve it. Secret missions were launched to recover fragments of crashed German missiles from Allied territories. Each recovered piece of metal told a story, of design, of material science, of vision. When the first complete V1 was captured largely intact, shipped to the United States, and laid bare for study, what those engineers saw was both frightening and inspiring. It was not invincible. It was replicable. And from that realization, a new project took shape. A coded effort that would soon lead to America's first jet-powered missile, known as the JB-2. But before that program could begin, there was another challenge, proving that the United States could master jet propulsion itself. A technology the Germans had already unleashed in the form of the Messerschmitt Me 262 jet fighter. That challenge would define the next chapter in aviation history and mark the moment when American industry began its relentless sprint to close the gap. At the height of World War II, American innovation lived in secrecy. Across the vast expanse of the United States, the boundaries between science and the military blurred almost completely. Engineers who once designed automobiles now calculated thrust equations. College physics professors found themselves consulting with generals. Every discovery, no matter how small, fed into the growing effort to respond to Germany's technological menace. At the center of this transformation stood two hubs of experimentation: Wright Field in Dayton, Ohio, and the Jet Propulsion Laboratory in Pasadena, California. At Wright Field, the Air Technical Service Command coordinated test flights, propulsion studies, and weapons evaluation. Meanwhile, at Caltech, a group of daring scientists led by Theodore von Karman and Frank Malina worked under the military's radar, perfecting jet propulsion theory. What had started as an academic obsession with rocketry was now a wartime necessity. Their task was daunting: build an American missile capable of matching, and eventually surpassing, the German V-weapons. The first step was understanding how Germany had achieved its terrifying success. By late 1944, Allied intelligence had already begun recovering fragments of V-1s that crashed in England. These twisted remains were carefully shipped to the U.S., where teams of engineers dissected them like surgeons studying a new species. What they found was both elegant and terrifyingly efficient. A pulse jet system simple enough to mass-produce, yet powerful enough to carry nearly a ton of explosives across 150 miles. It was, in a sense, the first cruise missile. Out of those findings, a classified project was born: the JB-2 Loon. The designation JB stood for jet bomb, and its purpose was clear: to replicate the German design, improve it, and test whether America could build a fleet of jet-powered missiles. Northrop and Republic Aviation were brought into the program, with Ford's Willow Run plant preparing to mass-produce the weapons. The timeline was almost impossible. Convert analysis into a flying prototype within a few months. The speed at which the program moved bordered on miraculous. Engineers reverse-engineered the pulse jet engine, redesigned the guidance system, and restructured the airframe for American materials and manufacturing. The Loon was not just a copy. It was a challenge answered. The first prototype took shape at Eglin Field, Florida. A sleek silver body, fitted with twin wings and a tail, resting on a catapult ramp facing the open sky. At the same time, other research paths branched off in secret. The U.S. Navy began exploring ramjet propulsion, engines that used sheer speed to compress air instead of moving parts. Bell Aircraft and General Electric were developing the P-59 Aerocomet, and P-80 Shooting Star, the first American jet fighters. And in the laboratories of the National Advisory Committee for Aeronautics, NACA, wind tunnels howled day and night, testing new engine inlets and turbine shapes. The mood among engineers was one of fierce competition, not against each other, but against time. Every test failure, every structural collapse or misfire carried the weight of lives lost in Europe. The war front might have been thousands of miles away, but the pressure was immediate and personal. Meanwhile, intelligence briefings made clear that Germany's jet programs were accelerating. The Me-262 was operational. The V-2 was striking London with devastating regularity, and rumors circulated of even more advanced designs: winged missiles, supersonic aircraft, weapons that could cross the Atlantic. Whether these reports were exaggerated or not, they added urgency to the American response. Within this fever of experimentation, the JB-2 project gained traction. The missile was simple, deadly, and scalable. Once catapulted into flight, it would cruise at nearly 400 mm, guided by a gyroscopic autopilot. Its pulsajets' roar, rhythmic and mechanical, would echo eerily like its German counterpart. Yet what made it extraordinary was not its design, but what it represented. Proof that the United States could compete in the new world of guided warfare. By late 1944, word of America's missile tests began circulating through Allied intelligence networks. The British, still reeling from V-1 attacks, watched closely. The Germans, through their own spies and intercepted communications, began to suspect that the Allies had cracked the code. The realization unsettled many within the Luftwaffe's engineering ranks. What had begun as Germany's technological advantage was eroding. Across the Atlantic, in dusty testing grounds and hidden labs, a new force was awakening, one that would soon stun the very men who had pioneered missile warfare themselves. And in a quiet corner of the Mojave Desert, the countdown to the first jet-powered missile launch was about to begin. Every major leap in warfare carries more than just technology. It carries stories of men who believed, of minds that risked everything to push the limits of what was possible. The American race to build a jet-powered missile was no exception. Beneath the polished aluminum and roaring engines lay a human story, a technological revolution, and a rivalry that stretched across oceans and ideologies. For most Americans, World War II was fought on distant shores, but for a small fraternity of scientists and engineers, the front line ran through their drafting tables, laboratories, and test ranges. These were men who slept beside blueprints and dreamed in equations. At Wright Field, Ohio, young propulsion engineers worked in cramped rooms, heavy with cigarette smoke and the hum of generators. They knew the stakes. Reports of the V-1 attacks reached their desks daily, accompanied by casualty figures and photographs of burning London blocks. Those images weren't abstract. They were motivation. Among them was Major Donald Kearn, one of the key Air Force officers overseeing missile development. He had seen firsthand the destruction the German weapons caused during his visits to England. His conviction was simple. If America didn't master jet propulsion now, it might lose not only the war, but the future of flight itself. At Caltech, meanwhile, men like Frank Molina and Jack Parsons, the founding minds of the Jet Propulsion Laboratory, blended academic genius with reckless curiosity. Their experiments often went wrong. Engines exploded, fuel lines burst, but with every failure, they learned more about airflow, combustion, and thrust. For them, the line between scientist and soldier blurred. Every success meant one less edge for the enemy. Working day and night, these teams embodied a new kind of warfare. One fought with mathematics and metal instead of rifles and tanks. They weren't building weapons out of hatred, but out of fear. Fear that the enemy might perfect the skies before they did. For centuries, flight depended on blades and pistons. The hum of propellers defined aviation. Jet propulsion shattered that tradition. It was not evolution, it was revolution. The pulse jet engine used by both the German V1 and the American JB2 was deceptively simple. It had no turbines, no compressors. Air entered through a spring valve, mixed with fuel, and ignited in rhythmic bursts. The result was a low-frequency roar, the infamous buzz that Londoners learned to fear. But behind its crude appearance was an ingenious concept: sustained combustion without moving parts. For American engineers, this was both challenge and opportunity. They realized that simplicity meant mass production. A pulsajet could be built quickly and cheaply, perfect for a weapon meant to be launched by the hundreds. The JB2's engine, dubbed the PJ-31, was a near mirror of its German counterpart, but slightly refined for American materials and fuel standards. Jet propulsion represented more than speed. It was the gateway to autonomy. For the first time, a machine could fly without human control, guided only by instruments and mathematics. The implications were staggering. In the minds of military planners, this wasn't just a weapon. It was a new domain of warfare. The shift from propeller-driven aircraft to jet and rocket propulsion also symbolized a philosophical change. Warfare was becoming detached, impersonal, and mechanized. Decisions made in laboratories now determined the fate of cities thousands of miles away. The weapon's pilot was no longer human. It was gravity, air pressure, and physics. While engineers bent over drafting tables and test racks, a different kind of battle was unfolding in Washington. One fought in conference rooms, war briefings, and memos stamped top secret. General Henry Hap Arnold, the architect of America's air power, was among the few military leaders who understood that the war's future would be written not by how many planes a nation could build, but by how fast it could innovate. Arnold had seen the reports from Europe, Germany's jet fighters, its V-1 flying bombs, and its relentless experiments with rocketry. He knew that America's industrial might would mean little if it couldn't compete scientifically. His message to his officers was blunt: "We can't afford to wait for someone else's discovery." Under Arnold's guidance, projects that once seemed impossible found funding and freedom. Laboratories at Caltech, MIT, and Wright Field operated around the clock. The Air Technical Service Command expanded its network of experimental divisions. He even arranged for captured intelligence, fragments of German aircraft and early jet components, to be flown directly to American test sites. To Arnold, jet propulsion was more than a war necessity. It was a symbol of national destiny. He imagined an air force that could reach any point on the planet, powered by engines that defied the limits of propellers. His vision stretched beyond the war, to the dawn of an era when the sky would no longer be a barrier, but a bridge. It was leadership rooted not in conquest, but in foresight. And it was that foresight that turned scattered experiments into coordinated purpose. The introduction of jet-powered missiles like the JB-2 Loon changed the logic of warfare. Until then, every weapon relied on human presence: pilots, gunners, bombardiers. But the missile didn't tire, didn't panic, didn't feel the cold wind at 20,000 feet. It was relentless. For U.S. military strategists, this weapon promised possibilities never seen before. Imagine a missile launched from the deck of a ship hundreds of miles away, gliding toward an enemy port with no pilot aboard. Or a salvo of jet-powered bombs unleashed from mobile launchers, overwhelming defenses before a counterattack could even begin. Even in its infancy, the JB-2 represented that future. It could travel up to 150 miles, strike with deadly accuracy, and be built for a fraction of a bomber's cost. Its launch crews needed no cockpit training, only precision in setup. Once fired, it was unstoppable. But this tactical evolution also forced difficult questions. How much control should a nation place in machines? What happens when speed and distance remove the human conscience from war? Military officers debated these ideas quietly, even as engineers celebrated their success. The JB-2 wasn't just a missile. It was the blueprint for a new kind of warfare, where automation and destruction walked hand in hand. The battlefield, once a place of human valor and sacrifice, was being rewritten by engineers with slide rules. As 1944 drew to a close, the world was changing faster than anyone could comprehend. The age of flesh and steel was giving way to one of circuits and fuel lines. And while victory seemed near, a shadow of unease spread among those who truly understood what was being created. The concept of an unmanned weapon, a machine that could decide its path, strike a city, and return nothing but silence, carried a moral weight that few were ready to face. Scientists who once saw their work as patriotic duty began to question its long-term consequences. Theodor von Kármán, one of the minds behind the American propulsion revolution, wrote years later that he realized, even during the war, we were opening doors to powers mankind was not morally prepared to control. His words echoed the same fears that would later haunt the creators of the atomic bomb. Strategically, though the Allies could not turn back, the only way to end the war was to outpace Germany, to win the technological race before the enemy's next miracle weapon reached the battlefield. And so, moral reflection gave way to urgency. Factories worked day and night, military test ranges echoed with explosions, and a new understanding of warfare was born. One that no longer required the human hand on the trigger. By early 1945, the JB-2 Loon had transitioned from experimental curiosity to a weapon ready for deployment. Hundreds were ordered, and test launches across Florida and California proved its reliability. Word of America's success traveled fast, across Allied command centers, and inevitably into the hands of German intelligence. At Peenemünde, when fragments of those reports reached the desks of engineers who once believed themselves untouchable, disbelief turned to shock. The Americans, they realized, had done the impossible. They had caught up. The hunter had become the rival. And the stage was now set for a turning point that would redefine the technological race of the entire war.